First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
'Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Okay, greetings, man, people. So we want to look at this negative 1/8 problem again. We just want to prove some of the things that we didn't formally prove in the first video. Now, what we did in the first video, we showed if we took partitions of 3 numbers, 5 numbers, and 7 numbers, all those results gave us an answer of negative 1/8. We also showed that by the way we divide them up, where we have a certain number of cutoff numbers, that the sum of the first partition would always be p squared, and the second partition would be 2p squared. And we followed up by showing the difference of any 2 consecutive partitions would be p squared, which means we can follow from p squared to 2p squared to 3p squared on off in infinity. What we didn't show in the first video, however, is that we would always get negative 1/8 regardless of the value of p, where p is any positive odd number. So that's what I would like to demonstrate here. So I want to kind of go back on the process. And so here I have some sequence, and I'm going to partition it off, and I have a relationship between p, the number of numbers in my partition, and c. So I'm going to start off by looking at the third example that was done in the first video. So in the first video, the third example, p was 7. And if you look here, when p is 7, this is 6/2, c is 3. That means there's 3 cutoff numbers. So that means that these 3 numbers will not be in the first partition of 7 numbers, and that means these numbers will be in the first partition of 7 numbers. And the sum of those numbers would be p squared. In this case, of course, p is 7, the sum of those numbers would be 49. And then the following sum after that would be 2p squared, and then 3p squared, and so on. And all that was demonstrated, proved formally in the first video. But we didn't prove in general about this particular sum. Now, this is a partial sum of an arithmetic sequence, and it takes to find its sum. Here, I mean, you can just add them up, but in general, it's the same formula we looked at in video number 1. So it's n/2 times a1 plus an. Now, the thing with this particular, our cutoff numbers are always going to start at 1. So our a1 for the sum of the cutoff numbers is always going to be 1. Our an is always going to be c. So c is the number of cutoff numbers, so that number will always represent the last number that are cut off. So that will be our an for our cutoff numbers. So if we want to do a partial sum for the cutoff numbers, now how many numbers were we going to have? We're going to have c numbers, because that's the number of cutoff numbers, obviously. C is p minus 1/2, so it's p minus 1/2 over 2, that's p minus 1/4. And again, a1 for the cutoff numbers will always be 1, and an will always be c, so p minus 1/2. So this will give us the partial sum of the cutoff numbers. So this would be the partial sum of the cutoff numbers, and this sum will always be followed by p squared plus 2p squared as follows. And of course, this is what s equals. So if we look at it, S is this sum here, p minus 1/4 times 1 plus p minus 1/2 plus p squared plus 2p squared plus 3p squared, and so forth. And so what we're going to do from here is we're going to do a little bit of algebra, solve for S, in the hopes of giving -1/8. So if we solve for S here and get -1/8, this means we will always get -1/8 regardless of the value of P, where P is any positive odd number. Okay, so let's see what happens here. Let's make these two guys have a common denominator. So I can turn 1 into 2/2, so that's 2/2 plus P minus 1/2 plus P squared plus 2P squared, etc. And now I can add these together. So this would be 2 plus -1 is +1, so that would be P plus 1/2. P plus 1/2 plus P squared plus 2P squared plus 3P squared, etc. Now we can just multiply this straight across. P minus 1 times P plus 1 is P squared minus 1. P squared minus 1. 4 times 2 is 8. Plus P squared plus 2P squared, etc. Now we can factor the P squared out of all these terms. So there's a P squared in all these terms, of course. So S is P squared minus 1/8 plus P squared. So if I take P squared from P squared, I get 1. P squared from 2P squared, I get 2. From 3P squared, I get 3, etc. And we know this is S, correct? So S is P squared minus 1/8 plus P squared times S. So now let's solve for S. So let's move the P squared S to the other side. It changes sign, so S minus P squared S equals P squared minus 1/8. Factor an S out of here. So S, this would be 1 minus P squared. 1 minus P squared equals, now I have 1 minus P squared here, so I kind of wanted to match this guy. So all I have to do is multiply this by -1 to make this become 1 minus P squared. So say negative 1 minus P squared over 8. Hopefully you can see if I multiply 1 minus P squared times -1, I get P squared minus 1. So now the last thing we need to do to solve for S is divide by this guy. So when I divide by this guy, on this side it cancels, on this side it cancels, there's a 1 there, and lo and behold, S is -1/8. So now we have proved for any odd number P, where P is a natural number, an odd natural number, that for any particular value of P, we will always get -1/8.